Good evening and welcome everyone to the Black Hole. Today we are going to discuss what are LLMs, that is large language models, how do they process responses to our prompts, and what are the challenges and future directions in the in enhancing these models and expanding their accessibility. Moreover, we will also discuss the exciting applications of these models in various domains such as healthcare and एजुकेशन। और इस मौजू पे गुफ्तगू के लिए हमारे साथ मौजूद हैं गौहर इरफान, जो मेरे दाएं जानिब तशरीफ़ फरमाए, PhD कैंडिडेट एट MIT एंड वन ऑफ mentors फॉर द ब्लैक होल्स रिसेंटली इंट्रोड्यूस्ड mentorship program. आप जानते हैं that this program aims to help and guide students in their academic career path. Gohar Irfan's research focuses on making cloud computing more efficient. He works with both software and emerging hardware technologies to enhance the performance of modern applications such as AI, while reducing resource usage like power and carbon footprint. Before starting his doctorate, Gohar worked at Microsoft Research, where he served on various projects to improve the resource efficiency of Microsoft's data centers. अब सब लोगों की आमद का शुक्रिया। हमेशा की तरह please do us a favor and turn your cell phones to silent mode so that there is no distraction. देखें, ये सारे सेशंस जो हैं ये आपकी लर्निंग और आपकी जो इल्म की कायनात है उसको वसअत देने के लिए, और वो आपकी शमूलियत के बगैर मुमकिन नहीं। प्लीज़ आप इस गुफ्तगू में ज़रूर शरीक होइएगा। अपने सवालात, तबसरे, जो भी आपके ज़हन में ख्यालात हों, जस्ट रेज़ योर हैंड फर्स्ट सो दैट दिस माइक्रोफोन इज़ गिवन टू यू। बस यही थी दो तीन बातें। नाउ let's learn about the transformative potential of these advanced language models and the impact they can have on our world. Please welcome Gohar Irfan. Thank you.
So the topic of the talk is peeking behind the curtains of LLMs. LLMs stands for large language models. तो मैंने थोड़ा सा deliberately एक spicy सा topic choose किया था because LLMs, आजकल एक hype topic है. How many people are familiar with what this icon logo stands for? ChatGPT. ठीक है. So people are familiar with this interface and people have used ChatGPT. ठीक है. So ChatGPT obviously for the past couple of years at least has had a lot of hype. People are using it for various useful / funny things. Some people are using it for writing their college essays, trying to even pass medical licensing examinations in different job applications and whatnot. But not many people actually know what exactly goes behind these language models. How do these language models work? So just as a nobody can see this and that's very intentional, but I asked, ChatGPT itself, what is a large language model? So who else can explain this better than a language model itself? At least that's the hope, that it knows what it is. So if you look at the response that it generated, and if we just skim through this and look at a couple of keywords, it says language models are advanced artificial intelligence systems. They have some sort of data that goes in. There's some notion of machine learning involved here, some deep learning, some neural networks. So all of these are very relatively famous buzzwords that we've heard around. Again, we don't all very deeply understand what these things are, and that's sort of the goal of the talk, to sort of decipher what some of these things are on a very high level, and then we can all go back and try to dig deeper into these things. Then it has this concept of training. So these models are trained on some large language models, presumably have large data sets that they are trained on, contextually relevant data. So when you type responses, usually they give you some coherent answers. Sometimes they're hallucinating, sometimes they're completely incorrect, but more often than not they give you some relevant answers. And these models have many parameters. So sometimes you see these news articles saying, okay, there's a new language model that has 100 million or even 100 billion parameters now. What exactly are these parameters, and is more parameters always better? So we'll try to look at these things. And then what can these models do? So they can do text generation. In the case of ChatGPT, they can do text completion. So we have our smartphones, keyboards, even on Google Docs and Microsoft Word, you start typing and it tries to autocomplete things. And also usually it's fairly coherent, and it tries to understand the context before it gives you the answers. And then you can do question answering. You can use these things in chatbots, language translation. So I write something in English, I get a response back in Urdu. That's also fairly possible. Educational tools like Khan Academy is using these chatbots to assist students in learning. and research and data analysis and so on. So there's many very useful applications of this technology. And then there's also some challenges. There's some biases involved when you're training these sort of models, like they're not always very fair in the responses that they generate, and of course that has implications to society, which is readily using these things. There's a challenge of interpretability. So if I ask it a question, why does it give me a particular answer? What went behind the entire training process that led to that particular answer? We don't understand these things very well. And even now, even with the advancement that we have today, we still don't understand these things very well. So these are some open challenges, some ethical considerations which we'll touch on towards the end. So some very quick guidelines on like what this talk is going to be about. So this is just an overview of large language models. It's very hard to comprehensively, again, it's not my specific area of expertise. So there's many research papers, and there's a lot of research actively going on. So it's very hard to cover this thing in like an hour and a half. But we'll cover some things like what are these models? What do these models look like? What's the infrastructure, like compute infrastructure that these models are trained on and then they run on? And then the future directions of where this technology is going in the future, right? And then hopefully you can go back and deep dive into subtopics on your own, and then you'll probably have a better understanding and better context on what is going on. And then finally, one small thing is to myth busting. So people talk about AI is going to take over the world and these kind of things, right? We look at what AI is, we look at some of the basics, and then you can go back and form your own opinion on like how much of that is reality and how much of that is actually myth. So we're only touching the surface today. Do not expect this to be a comprehensive talk in any regard. The idea is to just peek behind the curtains. So that's why the title of the talk. So first we'll talk about the model architecture. You must have seen, some of you might have seen these sort of weird looking pictures which have these block diagrams of inputs going in and then some magic happening and some outputs going out. So you type your prompt, out comes a response, right? So what exactly happens in this model architecture? We'll take a look at this. We'll take a look at the infrastructure. So you might have seen like these giant racks of servers that have thousands of machines doing some computation. What exactly are these machines? We'll touch upon that. And then the big open question of where is this technology heading? So broadly, we'll try to cover these things. I will be very hard pressed to spend equal time on all of these things. So we'll sort of look at the intuition behind these things first, and then as time permits, we'll touch upon the other aspects. So again, as the answer previously showed us, there's something about artificial intelligence. There's something about machine learning. There's something about neural networks and LLMs. So all of these are short forms for those things. So I intentionally use these here so that we are familiar with these things. But what is the landscape? So artificial intelligence is a buzzword, and it's a very old thing, by the way. So it gained traction recently, but this is like a very old field of study and piece of technology, which includes machine learning as a subfield. So this includes like image recognition and OCR technology that has been around for like decades. The reason that we talk about this more now is because we have the compute to do these things very efficiently on our cell phones and relatively cheap hardware. That's why it took off in the past couple of decades. Neural networks is one form of machine learning. So this is sort of like a Venn diagram of, again, not a very accurate Venn diagram by any means, but just to get a sense of the landscape. And then there's deep learning, which is a sub-form of neural networks, which we'll touch on this a little bit. And then finally, it's large language models. Right, so this is roughly the lay of the land. So LLMs are one small part of this whole field of artificial intelligence. So before we go into LLMs, we'll try to get some context about these things here, and then we'll touch upon what LLMs are. So before we move forward, how many people here are computer science students or know something about programming or machine learning or data science? Great. How many people have done some high school math, like multiplication, addition? So I don't believe you, sir, but everybody else I can. That's great. So I think more or less we just need like some basic high school math, and that should be enough to get some intuition behind these things. And with that, we can sort of go deeper into this. So we'll start with the architecture that I talked about earlier. So neural networks are roughly this black box, or a green box in this case. You have some inputs, you throw them into a network, and out comes some number, let's say. right? And so a very typical, if you open any like machine learning, data science, AI textbook or a blog post, like the usual example they start off with is like, I'll give you an image and the neural network will somehow tell me if this is a cat or a dog, right? So I'll start with the picture of my cat. So you put this in the model, some magic happens, and then out comes some probability which the model thinks it's a cat. So in this case, the model is 93% sure that this is a cat. And that's a reasonable guess because this is indeed a cat's picture, right? So the question is, how does a computer actually understand, decipher this image of a cat, put it into the model, and get that probability out, right? So that's roughly what we'll try to understand first. And then we'll go into sort of the language models. So, images roughly are just a bunch of numbers, pixels, RGB values, so like red, green, blue. They have different, let's say from 0 to 255, you can scale them and so forth, but pictures are really just numbers the way the computer sees them, right? So we observe them as images, but really it's just a composition of different numbers. So you split those numbers up, let's say into a nice grid, and then you feed these numbers in some fashion, in some pattern, like maybe 4 at a time or the whole image at a time, and depending on what your model is, and then the model is going to try to understand those things. So this is probably a very, very naive / simple quote-unquote neural network. And the thing to take away here is that it's sort of some neurons, which is these circles in the middle. They have some, let's say, connections or synapses, if you're sort of inspired by the biological terminology, that connect these neurons. And this is really just a composition of different neurons connected in a particular fashion. They don't necessarily have to be connected in this particular fashion. Maybe this one is only connected to this one is connected to all of them, and so on. And then you run through these numbers, and we'll see what they actually do, and out comes a probability, right? So there are many questions that might arise, like what are these numbers? Who tells you these numbers that lead to the correct probability? And what are you doing with these numbers? Like, how do you process these numbers to get that answer, right? So these are some very obvious questions to ask, and we'll try to get some intuition behind that. So any questions on where this is going? And have people seen something like this before? Cool. By the way, if any point there's questions, please feel free to shout or raise your hands or anything. But let's keep this very interactive. So if there's questions, I don't want to keep going. If there's questions, we want to address those questions before we move forward. So for those of you who haven't really seen this kind of picture before, let's take a closer look to see what exactly is going on, right? So we'll simplify, we'll ignore the rest of the network, we'll look at the inputs and one neuron and see what's going on there. So again, the image is just a series of numbers. We pick, let's say, this little strip of the image, which let's say in this case is 0.5, 0.3, and 0.6. We don't care what these numbers really mean as individual numbers, but there's some representations numerically. And they get multiplied with certain weights. So the inputs, the X or the blue, is these coming from the image. There's some weights that are shown in green here, the W's, and some operation happens that gives you this Y, right? And there's another number that's being fed, that's the B. So if you look at the equation on the right, all that is saying is you multiply the weights with the X's, you add that term B, which is a bias. Let's say we even ignore that for now. And we compute a summation of these numbers, and then we pass them to a function f, right? So not sure if this works. Yeah, this f. And we'll see what this f is, but really this is a summation of these. This is a multiplication and summation of these numbers. So these weights with these inputs x. That gives us this number y. And really this is sort of the building block behind neural networks. So this is essentially just a weighted sum of your inputs and some weights. And we'll talk about where these weights come from. But assume that these are just random numbers, right? So this is just a multiplication between these numbers and then an addition to give you this neuron. Now, this function f is some nonlinear function. We can also ignore this if we don't completely understand what this is, but really the idea is that linear functions can only capture so much information. So you need some sort of a magic function. We'll maybe see a couple of examples of that can sort of better understand and better capture what's going on to represent this data and sort of to understand this image better. So if you again zoom out, this is roughly what the neural network is. So we saw one of these in detail, but really the neural network is a network of these neurons. And it's loosely inspired by how the brain works. I am not a biologist, so I don't know if that's true or not, but this is roughly the same principle. So you have some inputs, like some let's say axons, they go through the synapses, something is activated, and then those are passed to further, let's say, neurons. Right, so there's a weighted sum which activates something after going through this function f that we saw earlier, and then out goes another value which is fed into some other neuron, and there's a whole cascade of these neurons. And that's the neural network. So any questions up until this part? Okay. So again, just to quickly cover up, so this is the same equation that we saw with minus the bias term. In this case, we have 3 of these inputs coming here from 0 to 3, and then go through these weights, out go some values. So essentially, a neural network is really, on a very, very abstract level, just a series of those multiplication and addition operations, which we call max. So multiplication, addition computations. There's a notion of going from left to right, which we call a forward pass. And then there's also a notion of going from right back to left, right? And we'll see what each of these 2 modes of computation are used for. So there's a forward pass where you have some inputs going in from the left, you do some number crunching, out goes some scores, and then in some cases you also want to go back and then repeat this process. So the main question now is, what is exactly, what is a good neural network? And there's no correct answer for that. So there's many different sorts of networks. This is just a small subset of them. You can have many, many layers of these networks. So that's where the term deep learning comes from. So if you have many, many layers, like let's say hundreds of layers of these neurons, that's the depth of a network. And then there's, of course, the width of the network, which is like how many neurons do you have in one particular layer. So you can have different neural networks. People keep coming up with different neural networks for different purposes. Some are for, let's say, recognizing like MRI images or audio detection and so forth. So depending on your use case and depending on sort of the model architecture and what compute infrastructure you will be running on, you can sort of tweak the architecture, but loosely, more or less, the fundamentals of each neural network are really the same. So again, in a forward pass, let's take some concrete values. So x0 is sort of, x's are the inputs, x0, w0, and then that gets fed to y0. And then y0 also has incoming connections from x1 and x2, so you do the same thing. So x0 times w0, x1 times w4, x2 times w8. You sum up all of these things. So these are the multiplications, these are the additions. So multiply, accumulate. That's really the fundamental operation that you all need to focus on. So this is really the backbone of all of these networks. And this is very important to understand, like, what exactly is going to run these computations. So we'll see how to structure these computations and why our computers can do these computations so fast and so forth. So all of these layers, all of these neurons individually are doing the same thing. So y0, y1, y2, y3. And it's just a bunch of sort of linear equations like this. So really, that was the green box that we had earlier, right? So that's a forward pass. So you have an input image that gives you some probability at the end after you do all of these multiply accumulates. Now, the big question is, like, how is the model learning these things? Was there a question? Okay. So the big question is, like, how is the model learning these things? Again, we don't understand why the image of the cat was actually giving us the correct label, right? And that magic really lies in the values of the weights. So that's where the training comes in, right? So the first question is, okay, if I run some inputs and I get some obtained value, is that value correct? So that's the training process. I give you some input images that are labeled. That's my ground truth. I tell you that these are images of cats, these are images of human beings, these are images of dogs, and so forth. And I label them for you, and then I feed those through the network. And after each image has been passed through the network, I will try to figure out, is the value that the model gave me actually matching the exact value? And these values don't necessarily have to be just binary, like whether it is a cat or no. It could be many different things. It could be like, what is, like, let's say I give you some complicated math equation, and is the answer correct, right? Is that the correct answer of this? If not, what was the correct answer of that equation, and so forth. So it could be many different things. It could be audio signals, and if you want to, let's say, decode those audio signals, like some value out of that. Is that the correct value that you were expecting? And so you try to compare the target value or your gold standard with the value that the model gave you. And you try to figure out, is there an error? And if there is an error, like what is this error? So in this particular case, I just use a very simple error equation, which is like the target minus the output squared, and then I divided this by half and sum this for all the errors, or all the values that I get from the model, right? And there can be very complicated error equations, again, depending on the use case, but we're trying to sort of simplify the things and understanding the principle behind it. And then you can use very sophisticated error equations, loss functions is also what they're called. So, and then we'll see how these are used. But again, before I move forward, are people sort of following? So that's where the back propagation comes in. So we saw the forward pass, which was like we fed something from the left, went all the way to the right, and we got a value. Now we're trying to go in the other direction, and the objective is to make the model learn some weights and learn something about the data that we're trying to really model with that neural network. So again, that's the error equation. The first step is you compute the error, or for whatever value or whatever input you used. And then the objective is to distribute that error back into the network so that each of the weights that you had get updated. So let's say you start with a completely random set of weights. You have 100 million, say, weights. Let's say those are the parameters. We generate 100 million random numbers, and that's our starting point. And of course, when you start with that, when you input a cat image, most likely it will not be able to accurately tell that it was a cat image. And using this, you iteratively, like one step at a time, or like one image at a time, or one batch of images at a time, you try to do this particular process. So you compute the error, you distribute the error back. And how do you distribute the error back? Again, we'll see that. And then in the next iteration, you sort of tweak your weights and then try again. And you keep trying iteratively until your model starts converging to some high accuracy. Question? So you, do you want to repeat the question for the microphone?
So when you compute the error, so then you will repeat it randomly?
That's a good question. So when you compute the error, I'll show you how you use the error to somehow slightly correct your weights.
Okay.
And then you try again.
Okay.
And then you see, okay, how much more accurate am I this time compared to the previous iteration? Am I going in the right direction? And these are things we'll talk about.
So if you again get the error, then again you will
you'll do the same thing. So the key thing is, like, the training process is an iterative process.
Okay.
You will not do this once, and you will not expect the model to learn after computing the errors once. You keep iterating, and then you based on like what your target accuracy is. Let's say you're okay with the 90% accurate model. You'll stop at some point, because usually like the error rate sort of starts falling down, and then it's very hard to push it, let's say, to 100% accuracy. So the rate at which your error is sort of fixing itself starts slowing down. So again, depending on the model, depending on the error function, all of these things can vary. Yes?
How do you put this error in the weight or in the equation? How you put this error?
I'll show you that just in the next couple of slides.
Okay.
Yep.
Who is there to set the target?
The target accuracy?
Yeah, accuracy.
That's also a good question. So that depends on several factors. It depends on your use case. So let's say if you're a doctor and you're trying to diagnose some disease based on some imaging, right? You really want your accuracy to be pretty high. You don't want false negatives or false positives, right? So depending on the circumstances, you will want to sort of adjust your false positive rate, false negative rate, or largely the accuracy of the model based on your use case. If I'm just detecting cats and dogs,
But
I might be fine with 80%.
But high accuracy doesn't mean that this is the correct one that is required by you. For example, if I get 99% accuracy, but
Right.
it may not be useful for me.
Because it's not 100%?
I need 100%.
Right, exactly,
and
exactly.
In that case, this is not the appropriate.
Exactly. So again, that's sort of the larger thing to keep in mind, is that it's very hard to get to 100% accuracy, because again, it's a probabilistic sort of a model, right? It's not ever going to be 100% accurate. You might be able to make it 100% accurate for a very, very narrow set of sort of input data, but if your input data, let's say you train a model now, and then you give it to, let's say, a doctor, right? And now the inputs could be anything in the world. Like you could have new scans, new images, which the model has never seen before in the training process. So then it's very hard to ensure that the model will, with 100% accuracy, give you the correct answer. So based on this, you obviously try to figure out, okay, is this acceptable for me? And then on top of this, can I have further guardrails? So let's say you have self-driving cars, right? They use.
Excuse me.
Yeah.
I didn't mean higher or the 100% accuracy as the ideal accuracy. I mean the correct accuracy.
The correct accuracy. I don't completely follow. So
If there is 99% accuracy you got
Yes.
as compared to 90%,
Sure.
then how I can get that this is correct one or not?
whether or
It-
not
it
this is
will-
acceptable to me or not.
Yeah, it may be possible that at 99% accuracy is not the correct and the result will be 0. For example, if I give this image to the computer or the neural network
Sure.
system, and if it says that this is not a dog,
Sure.
it means the accuracy, if it is there as 99%, but resultantly the answer I got is
Sure.
simply 0 because it is not correct, it is incorrect.
So if I understand your question correctly, so the accuracy fraction that you'll get is, all it's saying is if you give it 100 images,
Yeah.
99 of them will be correct, will be correctly labeled as cats. So let's say if you give it 100 images of cats, which you know for sure that they are cat images,
Yeah.
the model will identify 99 of them probabilistically as cats. The other one it might not correctly identify. It may or may not identify, right? That's what roughly the accuracy term here means.
Okay.
So it's not something for an individual sample. All it's saying is like if you have a set of samples, 99% of those samples will be correctly identified.
Okay, is there any post-evaluation criteria on it?
Again, that depends on the use case. So if you take a little bit more of a sophisticated example, let's say self-driving cars, right? They use a lot of these models. So let's say you've seen videos of Teslas driving around, right? And what they're doing is they have different input cameras, and they have these models running very sort of in a tight loop. And all they're saying is like, if there's, let's say, a pedestrian in front of me, stop. Now, in that case, if the model predicts inaccurately, there can be an accident. So in that case, you will put something, a post-processing, like you have one model, then you have another model, and you take, let's say, an average of the two models. So even though one model is saying there's no pedestrian, but in reality there is a pedestrian, even if the other model is saying there is a pedestrian, you will, again, in this particular situation, you want to be more conservative. So you will probably hit the brakes, right? So you can have a collection of models, you can sort of do a sampling from within models, you can use different inputs. So some might use input images, like from video streams, and then some infrared streams, and do a sort of an average of these different models, different input streams, to get to your final sort of outcome. So that's how you sort of try to work around models which are inherently not always correct.
Okay, thank you.
Yeah, more questions? Okay, so you do this, you get the total errors, and then you do and then you sort of update the weights. And so we'll quickly see how you update the weights. Okay, and again, just to quickly finish off on this. So the error function, again, this might not be the exact same error function here, but the error function is something loosely like this. And if you've seen sort of curves of different functions, all this is saying is, as for different values of the weight, the loss or the error is decreasing, and then it's going back up again. So you want to find the point where the error is the smallest, right? And so again, if you trivially think about this, you can sort of do a derivative of this where the derivative is 0, that's where your weights are, right? But again, in practice, that's not how it works, because the error functions are not usually as simple as this. They're not as sort of straightforward to differentiate or find derivatives for. So what you do is you do a linear approximation of sorts. So you find a small gradient and you figure out which direction to go to. So I'll say, okay, I'm here right now. This is clearly not the ideal spot to be in because my error is non-zero or fairly high. So I want to go down a little bit. And that little bit is sort of you update your previous weight. So all this is saying is the weight in time t plus 1, or like the next iteration, is the old weight minus some learning rate multiplied by this differential of the error function. So you update the weight a little bit, and what the little bit is sort of is defined by this learning rate, and then you try again. And so the objective again, or the hope is that you'll land somewhere close to this minima, and that's where your model should roughly be. So again, this is a very, very simplified example. This is not how these sophisticated models work, but again, the principles are roughly the same. So how do you do this? Again, you have these models with multiple layers. That's roughly when you get the output, you compute the error, and now you have to distribute the error back, which was one of the questions, like how do you do this? So you have the error term, you took the derivative, and then you want to sort of say, okay, how do I adjust, let's say, this particular weight? So there's a weight here, there's a weight here, there's a weight here, and there's a weight here, right? So whatever error I got, what was the contribution of this weight to that error? How do you distribute this error, and how do you correct these individual weights based on that? So what you do is, again, let's not go very deep into this sort of calculus here, but roughly the idea is you took the derivative, and then you want to sort of distribute this. So all this is saying is if the loss function, let's say that's L, if I do a derivative of the loss function with respect to this particular value of the weight, let's say this particular value here, that depends on the value that it output in its neuron, which was the y value, and then the derivative of y with respect to that weight, which is really the chain rule which we did like in calculus in college or high school, right? So again, if this is something that people have to recall, really the idea to take away from this is you do a derivative and then you sort of distribute this derivative based on the chain rule, and you figure out how much the contribution of each weight is, right? And that's how so again, the y equation in this case is fairly straightforward. All it's saying is it's a multiplication of the weights with the inputs, which is what we saw earlier. So you just do a derivative of that, turns out to be x. And then you plug those values in, you get your remaining with this particular value. So all this is saying is now, in order to find the derivative of the loss function with the weights, you have to find this term, which is the loss function with the particular, the previous input activation times x of I, which was the input value for that neuron. And you propagate this back. So you do this for the previous layer, and then you do that for the previous layer, and so forth. So as we saw earlier, you'll keep doing this for each weight in your neural network, and that's how you adjust that for one iteration. And then you start again, then you do the process again. So does that answer the question that people had? Okay. So now the question is, okay, we've seen how we can visually represent this data and how we as humans can sort of make something off this data, or how this network works. But how do computers process neural networks? How is all of this going to be mapped to the infrastructure that we have of many, many servers, many, many CPUs and different accelerators? So recall that this is how we were representing neural networks, it's just a bunch of linear equations, right? And so for the computer to process this, there's a very efficient form in which you can represent this computation, which is you can represent these things as matrices. So we can see that all of these x zeros, or this particular neuron, the input, can be plugged into this vector here. x1 can go here, and x2 can be the last entry. And then similarly, all the weights will go to a separate matrix. And now you can basically represent this as a 1/3 matrix, this as a 3/4 matrix, and that will result in a 1/4 resulting matrix, right? So effectively, if you do a multiplication in accumulation to find out the value of this entry in the resulting matrix, that looks identical to what we had here, and so on for the other ones. So really now you can represent, instead of doing these individual linear equations, what you can do now is just do a matrix multiplication to get the final output for all of them. And why is a matrix multiplication the right way to do this? The long story short is we have developed sort of accelerators which we call GPUs. I'm not sure how many of you are familiar with this. We'll take a look at that also, which are very, very good at doing this sort of math. So as opposed to doing these equations one by one or sort of parallelizing this operation, they're very, very good at doing many of these, I mean hundreds and thousands of these simultaneously, very quickly. So if you can represent your computation in this particular form, then you can do the forward pass very quickly. So now the forward pass is really just two matrices being multiplied. So before we go into what sort of the remaining pieces of the large language model are there any more questions?
Whether it influences the mechanism of processing in the neural network or not?
The short answer is you can represent many different things. Again, you can sort of do a pre-processing phase and represent all of them as numbers. So you can represent images as numbers, you can represent like language, words as numbers, audio signals as numbers, and then roughly the process is the same. Now, how you tweak the weights and what architecture, what specific depth or what specific width works better for each of these modes depends. They're sort of sophisticated models specifically for audio, specifically for language, and so on. But again, the principles are roughly the same because you can map all of these different inputs as numbers. And so I'll show you quickly an example of how language can again be transformed as numbers. So images we saw as like pixels have numbers. Language can also be represented as numbers, and then you're basically doing the same thing. And again, the thing to take away is that these networks are really a form of compressing data. So you can think of this as a lossy form of compression, right? So what you're doing is you map your input in a high dimensional space, and then you're trying to sort of do pattern matching on this. So you do, again, for cats, you take some features like one by one. Let's say you look at subsections of the image, and you're trying to figure out like which of these features, like sort of I've seen these before in some high dimensional space. And again, the thing that I was talking about earlier where you as human beings cannot interpret what the model is doing is because it's a very, very high dimensional space, like hundreds of dimensions. So for us as human beings to reason about why it thinks something is a cat or a dog is relatively hard to reason about, because in some high dimensional space, in some 800th feature of this image, it thinks it's actually a cat. And so that's how the model is learning, but we don't exactly know which feature it's sort of trying to match when it detects something. So we saw most of these things that the prompt gave us, artificial intelligence, neural networks, and so on. But the two things that I sort of ignored intentionally earlier was transformers and attention. So specifically for language models, these are two keywords that are sort of important. And attention is all you need is a famous paper that came out in about 2017 that sort of introduced this concept of transformer models that is very good at doing sort of ChatGPT style computations. And so we'll quickly see what, in addition to what we already saw, makes language models so accurate. So to answer your question, so now we have, instead of images, we have like a sentence or like a subset of a sentence. So cat sat on A, right? So I put in 4 words. The input, that's my input context. It's 4 words. Again, I'm mapping these to these input neurons. I'll do some forward pass, and now the task at hand is to predict the next word. Okay, and in this case, the model is predicting cat sat on a mat, and it thinks 97% chances are that that's what you meant, right? So on the basis of available data? On the basis of the available data, yes. It's highly dependent on what data this was trained on. So if the word mat never appeared in your input data set, then you obviously cannot predict that. But based on many thousands, hundreds of thousands of input tokens of the World Wide Web, Wikipedia, and so forth, these models are trained, and then they're able to sort of fill in or try to predict what you're thinking, roughly. So again, how do you represent these things? So you have cat sat on A. It's a string. I tokenize this string. Let's say I just tokenize it by the space character. So now I have these four words. I turn these into numbers. So very trivially, you can think of this as I have a key value mapping. I say, okay, all the whatever 50,000, 60,000 words in my dictionary, starting from 0 to 60,000, each of them has a unique number associated with it. So I can say, okay, cat maps to 101, and so forth. And that's how I'm able to obtain a numeric representation of these words. So this is my dictionary. Roughly, you can think of this as like keys and values. So words have some numbers associated with them. That's not exactly accurate, but for the sake of simplicity, we can sort of go with this. And then you do something similar. You go through some process of weights, and you get something called a query vector, a key vector, and a value vector. Okay, so you note that this is a vector of numbers to begin with, and then you do some processing on this, and you get 3 more vectors out of that. And so this is going to lead us to the concept of attention. So what this is saying is, the query queue is roughly based on your input tokens with some post-processing. You have these different keys, which is your dictionary of words. So let's say this is all of the English language words, right? And what I'm going to do is I'm going to try to assign some attention to each of these words. So based on my input cat sat on A, I'm trying to assign some number that says which of these input words are these words closest to? So which words should I pay attention to from this very long input prompt that you've given me? Not in this case, but like that's typically how we use ChatGPT. Which words should I pay more attention to when I give you the output prompt? And so I do that, and then I do some scaling on this, and I get some values out. And these values, roughly, you can think of this as the output prompt that or after some post-processing, it's the output prompt that it's giving you. So again, you can sort of ignore the math, but the intuition is you have some function, alpha here, which is a function of your query and your keys. You do a product with the values. Again, keys and values are your English language dictionary. The query is what you give in as a prompt. And based on some weights that it has learned, again, similar to how it was learning what cats and dogs are, it's learning which words in the English language are more similar to different words. And if you give me a sequence of words, what is the relationship between these different words and where are you going to predict the next word? So that's roughly what the learning process is going to give you, which is your weights. And then it gives you some outputs. So again, it's a multiplication of the query with the keys divided by the length, just to normalize things. E is the length of the vectors here. And it gives you, softmax is a function that says, I'll give you some number of values, and all of the values should sum up to 1. So now I have a dictionary of words. The output is going to be a probability of what the next word is going to be. So the probabilities should sum to 1 of the entire English language, and you'll pick the one that is most probable to be the next one. So that's roughly the intuition behind this. And
where did the exponential come from?
where did the exponential come from? That's a good question. This is part of the softmax function. Again, not a theoretician, so I cannot give you for sure why they're doing exponentials here, but this whole term is meant to scale things between 0 and 1 so that the sum of all the values is 1. Why the exponential is there is more of a theoretical question that I cannot answer, so I will not even attempt to go there. If somebody in the audience has an intuition for that, that could be great. So normalization is this part. So what this is saying is like you multiply this and you sort of divide by the length of the vectors. So that's one normalization, and then this is normalizing so that you don't go beyond, like all the values stay within 1, so that when you sum them up there, the answer is also 1. But this exponent is, I'll have to get back to that.
So E is the length of the query?
The capital E is the length of the query vector, yes. Okay. And this, again, can be mapped into matrix multiplications. So in the previous case, what we saw is we have one query vector, which corresponds to one set of words that one user has input. At the scale of, let's say, ChatGPT, where you have multiple users doing this simultaneously, what you'll do is you'll concatenate those queries into, instead of a single vector, you'll concatenate those into a, let's say, a matrix of multiple queries, either from the same user, multiple users, and so on. And then you'll run this as a matrix multiplication operation. So you have these inputs, again, even for a single query, you have this input that you gave, cat sat on A. You have this set of weights that you've learned. You do a multiplication and you get these query, key, and value matrices. And then you pass them through this attention mechanism, which results in this output, which is going to be.
So you're going to miss out on some actual physical situations, like the cat sat on a rat.
Exactly, yes.
Now,
100%.
It's not likely, but it's possible,
It is possible.
that it would sit on a rat.
Absolutely. So the key thing here is the concept of the context. So if, let's say, you given a prompt to ChatGPT that says, I am sitting in a room where there is a cat and there is a rat, and there is no mat, and the cat is approaching the rat, and then you say cat sat on A, there's a high chance that it will actually give you cat sat on a rat. And that's because of the context. So if you go back to the previous slides, so we had, the context here was just 4 words. So it's important to sort of note that when you give an input prompt, the language model has some number of tokens from the past that it will use to give you the next answer. So if there is a concept of a rat somewhere in the input prompt and it's let's say the model is looking at the past 1,000 words, and if that context is there somewhere in the 1,000 words, then it will try to figure that, it'll try to sort of map that onto the final output. Because that token will be processed with the neural network. So somewhere, again, in the high dimensional space, it'll try to find, okay, this input token needs to be matched with something. So the probability of giving you a rat will be higher because a rat was in your input context. But yes, that is absolutely possible.
If we put, it means that this takes the most probable case from the known data available
Yes.
on the net.
Yes. So it gives you the most probable case from the known data as well as the input context. So the key thing here is that for language models, the input context is very important. So it'll try to pay attention to things from your input context. So for example, here, again, this is a very, very simplistic kind of a picture, but your input query has, let's say, a rat somewhere here. That will be mapped with all the other keys using this attention function which it has learned. So this is like the high dimensional space that it's learning. So if you pass in some information in your input, then there is a fair chance that it will be sort of captured by this attention mechanism because it's looking at the previous context that you provided. So you're telling it that I have a cat which is very close to a rat. So it's trying to sort of capture that. Yes.
Rat chases cat.
Uh-huh.
Then how it would respond to this?
Again, so
Concept,
that's a great question. Again, so what I'm saying is that it's a combination of your input context and the context that it's trained on. So if you in your training data you keep telling it that rats will always, let's say, eat cats or whatever, right? Or rats will attack cats, something like this. If that's the bulk of the data that it's trained on, then when you try to tell it that, okay, there is a cat and there's a rat in the room, then it will try to use that input context with your input prompt to find that out. So if in that case, I mean, if the ground reality is that a cat can never sit on a rat, maybe there's a high chance that even if you tell it there's a rat, it will not give you rat as the output, right? So it's a function of all of the corpus of text that you were trained on versus, in addition to the input context that you gave it.
Meaning is basically the byproduct of syntagmatic and paradigmatic relationship, whereas your model bases on the linear composition.
This is the linear composition,
Yeah.
except that there's some nonlinearities that you put in your model in some stage. So it's not just a linear composition. So there's linear compositions here, but I'll show you a picture again where there's nonlinearities in the model to try to make sure that you're not just learning linear relations.
Don't you think that these models, without having the context, are claiming for the contextual information there?
Sorry, say that again?
When we don't have any context and decontextualized version of information is there,
Yes.
and we are trying to getting this contextual version of meaning, how is it possible by these machines or these softwares?
Again, if maybe I didn't get your question completely, but if you're saying that if the input has no context, or if the data that it's trained on has no, like if something has no context to the input, then
Can I explain?
yeah.
For example, cat is the first word,
Sure.
and then comes the verb
Uh-huh.
in English.
Sure.
And this verb is basically a paradigmatic choice. There may be hundred of
Sure.
million or billion
Sure.
of choices are there.
Sure.
This is what that makes semantic in
Sure.
the context of the syntax.
Yep. So
But
yes.
this is missing in your model when this goes for this exponential part of the meaning.
So, okay, let me summarize how I understood your
Okay.
question. So you're saying if I just so the task is to predict the next word. My first word is cat, and now I wanted to predict the next word. It could be any number of things that come next, right? So in this, where the context is basically nothing, like your only input is the word cat, there's no prior input context that you gave, then the output depends on the context that it was trained on, right? So as you said, like in the English language, typically whatever words come after cat, there will be a higher probability associated with all of those words. And then depending on how you make a selection, again, that's a knob that you can tweak when you're developing the model.
in an example to explain it, green ideas sleep furiously. Syntactically, this is well-formed sentence, but semantically, this is simply fuzzy.
Okay, we can take this offline.
Okay.
I'm probably not getting the details of your question. More questions? Okay. So to sort of sum up, we have these input embeddings, we have this concept of attention, and then we go through some other layers similar to what we saw in the feed-forward network, and that's roughly what forms a language model. So we looked at these attention mechanisms, so you can have multiple cascading identical similar small models that all pay attention to different things in the sentence and try to look for different things and do different pattern matching, collectively giving you the final output. And each of these attention mechanisms is, again, roughly matrix multiplication, a dot product scaling, softmax, and then more matrix multiplications. So again, the takeaway from this is the crux of all of these models are really just these matrix multiplications between the query, the key, and the value which you obtain from some learned attention weights. Okay? And so you can do many interesting things with this. So if you have like multiple words, how does that work? Well, you predict one word, then that becomes your sentence. Again, you do the same thing, that predicts the next word, and so on. So you keep cascading these things, and then that's how you get like multiple words responses from things like ChatGPT. So now that we have some intuition about how these things work, of course, this is not a very detailed or complete intuition, but some idea of how these things work, let's look at like what sort of compute infrastructure is required to run these things. So how many people know what stock price chart this is? Can people take a guess? Do you have a guess? So can you guess what company's stock price chart this is? This is a stock price chart that is showing the price of some company's stock for the past 1 year, and it's growing pretty fast. NVIDIA. So the question is, what is NVIDIA making that is so hot right now that the stock price is going like crazy? They're making GPUs. So this is the picture of the latest GPU that NVIDIA is making. So the question is, why is this relevant to language models? And ever since language models came about, why did the stock price of NVIDIA and why are these GPUs so in demand?
Because we have to do the parallel processing.
Right.
In this. So to help out this, we need the GPUs for high processing.
Right. So the question is the answer is absolutely spot on. So we need massive compute and we need to do parallel processing, which is what these things are very good at. So the question is, what other things are these GPUs used for? Or before the language models came about, what were these GPUs being used for? These are very old. This is not the past like 2 years. For gaming and graphics. So these things are very good at doing calculations which you can sort of, again, map as matrix multiplications. So in the case of gaming or like video generation, it's effectively just pixels, and you're doing some computation on pixels, and pixels are just matrices, right? So that's why these things were a very natural choice of how you process language models, and that's why these things are selling like hotcakes now. So the quick thing to take away is these things are really beefy. And when I say that, what I mean is like, if you look at the teraflops that these things can do, and what teraflops mean is tera is 10 to the 12, floating point operations per second. So if you look at all of these numbers, roughly what this is saying is how many numbers can this thing process per second? So you can process 19.5 into 10 to the 12 per second. That's a big number. And the question is it doing this efficiently? And it's doing it fairly efficiently, but even then, it takes about 400 watts of power, one of these GPUs. And one of these things costs about $25,000, one of these. So if you look at one particular server, which hosts this graphic processing unit, which is what the GPU stands for, roughly half the power is being consumed by this device. And one server, typically, if you look at like, let's say Microsoft or AWS or these cloud vendors, the servers that they're using have about 8 of these GPUs. So 8 times 4 times 2, let's say roughly it's like 6,500 watts that one of these servers is using. So that's a lot of power that they're using. And then, of course, you can ask the questions about, okay, what's the carbon efficiency and so forth, right? So these are very beefy machines. Roughly, it's a n-dimensional matrix. So these are tensor processing cores, is what they call them. And then again, they have high memory bandwidth, which is they can very quickly move your matrices from memory onto the compute units, do the processing, and then do this over and over again. So these are very efficient for this. And again, as you mentioned, why are GPUs used? Because they're very good at running many processors, small processors that can do the same thing very quickly. So single instruction, multiple data. So I'm saying, here's a matrix, multiply these two matrices, and each tensor processing unit, which thousands of these are inside one GPU, are doing it for different chunks of data at the same time. So they can do the same thing on a lot of data at the same time. That's what makes this very suitable. So again, quickly for context. Now, how many do we need to run to, so let's say, train ChatGPT? So ChatGPT is a variant of GPT. GPT stands for generative pre-trained models, pre-trained transformer models. This has 96 layers. So we saw, 2 or 3 different layers in the small examples that we ran through. This has 96 layers, and they're fairly wide. So they have about 175 billion parameters. So that's how they're able to capture, a large corpus of data, which is roughly 45 terabytes of data, which has 300 billion tokens. And the data is, scraped from the internet, books, articles, Wikipedia entries, and so forth. And it's doing 3.14 into 10 to the 23 flops, floating point operations, for training. So one GPU is definitely not sufficient for this. And if you do sort of some back of the envelope calculation, if you have one of roughly of the same NVIDIA GPU, not the same one, but roughly the same NVIDIA GPU that I showed you earlier, it'll take you 355 years to train one ChatGPT model. So if you, again, extrapolate how many you need to sort of train this, it costs about roughly 4.6 million to train ChatGPT 3, and now we have ChatGPT 4, which is, I think, an order of magnitude larger in each dimension. So 1 trillion parameters trained on, I think, 10 trillion tokens, and it costs way more. So the reason behind me saying this, and we can sort of roughly skip this, but the idea is like sort of in the past, say, since the 60s to now, the demand for compute roughly has been growing like very fast. And this is a logarithmic graph, so you can sort of see that it's been doubling nearly every 3.5 months in the recent past. And this is roughly when this is probably before LLMs, but this is roughly about when LLMs were starting to take off. So this is before like neural networks like AlphaGo, who is sort of solving the game of Go and game of chess and so forth, and image classification and so on. So again, the summary is compute is hot in demand. Now, this begs the question like, okay, what is the repercussion of doing all of this compute? So something to think about is like we're going after these models. Are they that much beneficial to society? Because this comes at a very steep cost in terms of the carbon we're burning, right? So this is an article that came about recently. So one transformer model, which is only 213 million parameters. So the one we saw is 175 billion parameters. So this is orders of magnitude smaller than this. Is costing you roughly about 2-ish orders of magnitude like carbon dioxide that a human being consumes. An individual US car consumes about 126,000 pounds of carbon dioxide. So this is about roughly 5.5, 6 times of that. And this is a very old model now, because these things are being developed very fast. So we have ChatGPT 3 and now GPT 4, so this plot will probably like go there. So something to keep in mind, and but what this really means in terms of infrastructure is that if anybody is sort of interested in working on these problems, these are very interesting problems to solve. So what I work on individually is like on the infrastructure side of these things, and how do you make new GPUs more efficient? So how can you squeeze out more compute from the same GPU, let's say? And then that's, again, a very simplistic picture. Like there's obviously other components. There's like CPUs, storage, memory, network infrastructure, and so on. So everything is very tightly tuned to make sure that you can squeeze out as much as you can, because we have thousands of these in a data center doing things like this. And this, if you don't do this sort of cleverly, the cost is too high. So just to wrap up, any questions about these things? Okay. So just to wrap up, what does the future hold? So one of the questions that we had was like, can these models process other things? Well, yes, these models, I think GPT 4.0 is what it's called. It's a multimodal model. So what that means is you can give it an image and an audio input and some text and just say, okay, here's an image of me doing this and some input to aid with that, and then you ask some question. So they can see, they can hear, they can sort of obviously process words all at the same time. So the context that we saw was only words, right? But now you have context that has words and images and audio and potentially video also, right? So how do you combine all of these things to still give coherent answers is already possible. With what accuracy, that's debatable, but it's already in the works. Then there's this line of work which is tree of thought. So again, a model is really just compressing information that you give it. It's unable to do reasoning. It's really just doing pattern matching fairly well, but it's still just doing pattern matching. But human beings also sort of reason about things, right? So if you give it one input, in your mind, roughly you compute a few things, and then you think, okay, what's the most reasonable one, and then you take it off from there, and then you do some more evaluation, and you read some output, right? So you have a chain of thought when you process or you solve some problem and so on. So people are working on models that think, not just do pattern matching or compare with existing things. So that's also very interesting. Again, this is not my area of expertise, so again, if somebody's interested, there's many, many papers that are coming out on this. And then, of course, this comes with a steep cost in terms of bad actors. So when you have models that are taking input prompts, you give it an image, you can hide some things in the image as pixels, which is not apparent to us as human beings, but you can very easily trick the model into doing something. Like the model might be seeing a cat here, right? That's very easy to do. So there are like diffusion models and so on that you can sort of poison the models, as it's called roughly, and you can make the models do certain things. And if let's say the model is now in a self-driving car and you bring a signboard in front of it that has a picture of a cat, but the model is thinking it's a speed limit, the car can do something that you don't want it to do. The car can speed up or something like this. So again, these are things that people are working on, trying to avoid these things and trying to figure out like why this happens and so forth. And finally, there's obviously open challenges. There's biases because you train the model on a corpus of data that you control. If you give it certain types of data, it'll give you outputs that align with that type of data, right? So there's many examples of models giving you racist outputs because the model is not trained on ethical, fair data and so on. We talked about interpretability. We don't know why a model gave a certain output very clearly. And then the final question is like democratization. It's very expensive to train these models. So only the larger companies which have multi-billion, trillions of dollars can train these models. But then what about us? We don't have that kind of money. So how do we access the training part of these models? How do we influence how these models are made and like what data these models are trained on and so on? We can use these models, but it's very hard to make these models accessible fairly to everybody. So that's again an open problem that people are working on. And so there's many, many other problems. It's a very interesting area which has many different aspects. We only saw a very small subset of these. So that's roughly what I have for today. If there's more questions, I'm happy to answer. And just before I wrap up, I stole many things from a course that I took and these articles and many other things. So many things are not my own. I just copied them with due credit. How many people are like working with language models like GPT? What do you use them for?
Fine-tune them and
Okay.
make around end-to-end applications, yes.
Like what kind of applications?
Like we've recently developed a healthcare application, and so we use them to only answer this, fine-tune about on our data, and people can query on about the health such things.
So what kind of models were you using? Like open source models?
Yes, open source. It's basically GPT-4 and then Hugging Face, and
I see.
that's more. Yes.
And how much did it cost you to pre-train? Pre-training is relatively cheaper, but
Yes,
relatively
basically
cheaper.
it charges on the number of tokens we are
Right.
utilizing. It's
I see.
percent, some cents on 20,000 tokens or something. It's cheaper. Yes.
Cool. What are other people? Any other interesting use cases that people are using these for?
What are the parameters for setting the parameters for these machines or the systems?
Oh, for the machines.
Yeah.
That's a very sort of open question. I think it's depends a lot on the company that is doing the training. So, for example, I mean, if you're asking about like what sort of how do you decide like how many GPUs to use, for example, that kind of thing?
Yeah.
That's usually a question of cost to the company. People are so some companies like Google, for example, have their own version of GPUs. They don't use NVIDIA GPUs, at least for a lot of things. They have their own thing called a tensor processing unit, a TPU, which they developed in-house. So when you design the algorithm, the model, the hardware, and the rest of the data center, like the network infrastructure and everything in-house, then you can do many optimizations because you can control like everything starting from sort of the size of the model, the size of the memory on the chip that you're making, so that you can avoid sort of extra costs of transferring data and so on. So these are small examples of like how you can design everything from the software to the hardware to the network topology and even to the sort of amount of power you provision to your data centers, like everything in-house. That gives you a lot more flexibility. So that's like one of the parameters that you can control as a cloud vendor when you're training these models.
If the syntactic pattern of a language changes,
Right.
whether there is a change in the parameters entering or not.
Yeah, that's a good question. So there's something called fine tuning, as he was mentioning. So fine tuning basically means you take a pre-trained model and then you roughly retrain it by freezing some weights and retraining some weights on a new language. So for example, people are trying to do this even for like Urdu language, right? So you have a GPT, which is trained on, I think, English mainly. But you take that model, you freeze mostly all the weights, which makes retraining relatively cheaper because you don't have to retrain, like you don't have to sort of do the back propagation on all the layers. You do it on a subset of final layers. And that is shown to work, good enough. So people are using that to make language models that are rooted in GPT, but for other languages like Urdu and languages that people in the rest of the world don't pay much attention to.
Can you explain to us what is generative AI?
Yes.
There's so much hype about that.
Yeah.
Or is it
So-
what is it all about?
Okay, let me go back to one of the slides. Okay, so generative is really a buzzword. All it really means is that as the model is producing outputs, it's consuming its sort of own inputs and generating new things. So GPT is a generative pre-trained transformer. So what it really means is like you give it some input tokens, it starts generating outputs, and then those outputs are used to generate new outputs until some condition is met. So until it thinks, okay, now the sentence is complete, or some number of words have elapsed, or something like this, then it stops generating. So that's roughly what generative models are. And then they're doing generative models for images also. So you have like, you give it a prompt saying, okay, draw me a picture of, a person sitting in a car. It'll start drawing that first with the person, then it generates, a car, and then some landscape, and then you give it some terminating condition, and then it stops. So I think roughly that's what generative models are. They keep iteratively generating output based on what they've previously outputted.
Gemini has
Gemini is the Google one, right?
yeah, Google
Okay,
one.
yeah.
So the size of their context window is 1 million tokens, and in the next version they plan to, release the newer version with
Yeah.
5 million tokens.
Sure.
So what do you think? Why do we need to have such a large number of tokens as input?
Right. If you look at these models, and if you look at multimodal inputs, so if you 5 million words in a sentence usually sounds absurd. Like maybe I don't need this long a prompt. You do need it. I can sort of give you a couple of examples. But if you're talking about other modes of input, like let's say I'm giving you videos, and look at the past 5 million, let's say, frames to produce some output or produce the next, let's say, 10 frames. In those contexts, I think it's very useful to have larger context windows. Even for like audio signals, like let's say look at the past 5 million seconds or something like this to produce the next, let's say 10 seconds of sample. In those, if it's not just words, I think it's still useful to have longer windows. Even for words, I think one of the use cases that they're doing is eliminating the need to fine tune. So what that means is I give you GPT without any Urdu, let's say. In the prompt, which can take now 5 million, as you said, words, I can give you enough Urdu tokens and then ask you a question at the end. And without training the model again, it might be able to give me a reasonable response in Urdu. Because that input context is now serving as some sort of a training data, roughly. There's a lot of complexity that even I don't fully understand, but roughly that's what they're using larger context windows for. So eliminating the need to retrain or even fine tune. Maybe there's more use cases, but this is the one that comes to mind.
I would also like to hear your opinion about this agent, cooperative agent-oriented.
Yep.
You know, this new thing that has uh, this crew AI and
That I'm not familiar with, but I get the idea of like agents. Yep.
yeah, these agents. So each agent is basically, it's based on some LLM,
Sure.
and they are cooperating with each other,
Yep.
and they have their own specialities,
Right.
and we kind of make a team of them,
Right.
and then we give them a complex task which
Yeah.
is distributed among them, and then they solve it together.
Yeah.
So to me, when I see this kind of thing, then I think that we are basically changing the way we do software engineering.
Sure.
So in the future software systems, we don't need to have a very complex kind of coding.
Yeah.
We have LLMs.
That generate code. Yeah.
They will
With
generate
Copilot
code.
and things like this.
Yeah, and the copilot and these agents will be cooperating with each other,
Yeah.
generating parts of code, and then
Yes.
making complex systems.
Absolutely.
What do you think about that?
So I think, in my view, I think that really is the way to make language models useful. So there was a recent paper that came out of Berkeley. It's like an article, not really a paper. It's called something along the lines of compound AI is the way to go, or something like this. I can share the link. And they're arguing for the same thing. So what they're saying is like language models, like ChatGPT alone, like if you go to the ChatGPT website and ask it questions, is not as useful. If you can make it cooperate with other tools that might not even be models, it can make it very useful. So for example, if you ask ChatGPT any simple like algebra question, it's very likely that it'll get it wrong. Because as we saw, there's no notion of it doing like thinking and doing processing math. It's just doing some pattern matching. If it sees that problem or roughly something like that problem, it might give you a good answer, but otherwise it'll just give you some gibberish answer, which it thinks is correct. So instead of that, if I can make ChatGPT output a piece of code that can give me the answer, but not sort of do the computation or call some third-party API like Wolfram Alpha or something like this, if ChatGPT can do that for me, then I can link this output into a calculator or like some Python program or some Wolfram Alpha API. That'll give me for sure the correct answer. So we sort of leverage what language models are good at, sort of capture some semantic information about the language and give me more language instead of solving things for me. And then I compound this with other agents, maybe other models, maybe other non-models, like simple tools like calculators or like Python programs or something like this, and then they give me more useful things. So I think, in my view, I think that really is the way to make these things more useful, because the way I see this is like this thing came out like 2-ish years ago, if I'm not wrong, like the official like ChatGPT launch. It had the very steep hype in the first few months, weeks, and then it sort of tapered off. Because again, I don't really use ChatGPT that much unless I'm doing something very trivial, like okay, give me a script to plot like something. I give you some data and it gives me a script, right? Beyond that, I still go to Google. I still search on the web for whatever interesting things, because I know that I can have some confidence in the output because I can sort of verify, okay, this is correct. It's not hallucinating, for example, right? So if you augment that and sort of try to, so there's another thing that's coming out, it's called retrieval augmented something RAGs, right? So they're sort of saying, okay, you look up something and you don't make up or you don't hallucinate, you only look up things from a given sort of corpus of data, right? So you train it on a large set of data and then you make sure that the output is actually from a within subset of correct data. Domain-specific data, right? So I think those things, augmenting these things with other tools, other pipelines of tools can make it more useful. This in and of itself, I think can only go so far.
I have a very, very simple question, simple main question.
Sure.
If we have a data for the words suppose in the dictionary, the whole data.
Yep.
If there's in parallel, we have a data language which is street language, which is not included in the text language of the dictionary, or it is not, put in on the
Right. The input.
internet or whatever.
Sure.
So this is not accessible to
The model.
demand
Yep.
model. So how that can it handle that?
I think it depends.
Because there's in audio it exists.
Yeah, yeah.
These words exist in the audio, like we have Lahori drama.
Sure.
There are so many words in
Yeah.
Punjabi which is not in.
It's not written.
In written, but they are used in a
Yeah.
very usual way.
Sure.
So how they handle it? Can that handle it in these models?
Again, I think if you look at multimodal things, that means that these models will be trained on multiple sources, not just text. You'll train them on, say, audio or video inputs also. In that case, I think they should be, because then it's just another token, right? Because you take some audio file, you chop it up into you do some like transcription on it, then it's just a bunch of words, and then you train the model using those words, and then the model knows. That's one way. If otherwise, I think the example of like a larger context window can help. So if there's a word that the model has never seen, but in the prompt you're able to somehow explain to it that, okay, this is a new word, this means this. Now give me a sentence using this word, right? I mean, somebody can try it on ChatGPT, but maybe it can actually, sorry, say that again? Inference, yeah, exactly. Then it can probably infer from the context that you give it how to use it, maybe, and then give you a sentence that is a reasonable sentence. So because of the fact that this has a concept of input context, and it has some notion of like, okay, which word to pay attention to. So this is like a new word. I have to use this new word in the sentence, so I might be able to do something smart with it, right? So the input context might help if something is unseen in the training data. But again, this is something we can try on ChatGPT and see if it actually works or not, or other models.
Okay, I will try to make it quicker. I have two questions.
Sure.
First of all, it's a very breathtaking session. The second one, the architecture part, was very interesting because I'm a student of finance, so
Okay, cool.
I didn't know all these facts and information. So I want to ask that on the product level, when we using a ChatGPT, so people suffering with dyslexia, some problem with text, it is very helpful, like for me as well.
Yep.
So what I'm curious about, it's at the end, it is art of coding, that all that AI hype, that ChatGPT, like your third part of this
Yep.
session was future,
Sure.
like where the question mark was,
Yeah.
like the question mark. This one,
Yeah.
yes. So
Challenge.
the second slide, yes, this one. So it is at the end of the day that all science, it is art of coding or programming, or what thing it is behind. Like when we see a stuntman doing stunts, we appreciate his skills
Sure.
and his training.
Yep.
And so when we see this ChatGPT on
Yep.
product level, we like use it.
Yep.
But we have this curiosity that what this science is. It is art
Yeah.
of coding, what this thing is.
So I think long story short is like we saw the sort of the mechanism of how the math roughly behind this, like how things are
Mathematics,
translated, right?
mathematics.
And then of course you use that, you use programming like coding to capture that math.
Okay.
You write it as a program that, let's say, does matrix multiplication at the core of it, and then, right?
Mathematics, this mean is like
I think the whole sort of genius behind this is definitely the math part.
math part.
Programming
math.
is like sort of a way to express that onto the machine, right? The infrastructure
Brilliant,
that you have.
brilliant. Okay, and then if we see the question mark,
Yep.
then we will be curious about the future.
Yep.
So nowadays, if we see that this thing become a meme, that the Apollo astronauts go to the moon with the 4 KB RAM. Now this thing become a meme, but at that time, it
Yep.
was like a very
Yep.
big something. Like what I want to say. So there is a famous movie quote line that computer ने इंसान को नहीं, इंसान ने computer को बनाया. So like in 50 years, this thing again will replace, a new thing will come and replace
Yep.
the thing. So
We don't know what that is.
what's the future and the reason why I ask the 4 KB RAM thing, we as Pakistani, where are we lacking to get update to the current world? So
That's a very hard question to answer.
like
Beyond my pay
so,
scale.
and
I mean, okay, the first thing that you said was like, okay, what's behind these is definitely math, right? So I think, okay, very low-hanging fruit is like, I think if we have solid math foundations, we can at least start to understand what's going on. I can't answer like what will fix things, of course. I think generally now these things are becoming very accessible.
okay,
So we can at least pick up a lot of these things and play with these things. I don't mean just like use these things, but
Okay,
really like,
okay.
you know, take the source code behind this, exactly. Discover how they work, take the source code, it's all open source, let's say not GPT, but like there's so many models that are completely open source. You have all the source code, you have all the sort of the math behind it. You can take that, learn how to use it, and then maybe if you have an idea, try something, you know, extend that to something, optimize something in it. So I think at this point, we're definitely lacking behind, but I think it's also a more optimistic way to look at things is like these things are very open for people to use. I mean, of course, they're very expensive to train, for example, or all these things, but like at least to learn how to sort of program with these things and what's going on behind them and extend them, for example, is relatively much, much easier than, I don't know, theoretical physics, right? So you can pick these things up. Many people are self-taught, like, programmers and so forth. So you can try to tweak with these things, and we should not sort of always keep saying like, okay, we're lagging behind. Yes, we're lagging behind, but these things are relatively on a level playing field in some sense.
Okay.
So we can try to at least catch up.
Sir, this Venn diagram you show earlier, it give an idea that how this all AI follow up with one another. So,
Yep.
sorry, I'm taking one more question, but yes, this one. So, as we see, there are too many models. Like there's now Grok AI and too many tools. As sir mentioned, Gemini. But ChatGPT still is like have a take the stage. So the Sam Altman and his team do something unique in this Venn diagram that it conquers the stage.
I think they have some sort of a first mover's advantage. I mean,
Okay.
GPT is not a new thing. GPT-2 and GPT-1 is like a very, very old
Okay.
paper came out like a long time ago. But they, I think, commercialized it in a fairly accessible way. They have they're doing something behind the scenes because GPT-4 is not open source. GPT-3 is not open source. The one that they're using is not open source, right? So whatever they're doing, I don't know what the secret sauce is, right? But of course, these models are not new. So anybody could have really done the same thing.
So green circle, the LLMs, the ChatGPT green circle is better than the other tools.
That's not for me to say. I
Okay.
think better is a very, how do you define better, right? Like maybe
Better, I mean, like.
it's easier to use for sure. Maybe
Okay.
it's more
Like
accurate in some
perfect,
cases.
perfect.
It's not perfect, but
Okay.
it might be more accurate in some
Popular.
cases.
Okay.
But there's like
Like
Gemini.
something we call today as AI, artificial intelligence. So all we know is ChatGPT. No one name Grok AI or Gemini or Bing Copilot. All say ChatGPT. So
That's maybe something like Google search. When Google came out, there's something similar that happened. Thank you.